Hello, so this will be the first meeting on the chapter 14 review. Something important about chapter 14, not all sections of the textbook are covered. However, there is also things that are not covered in the textbook, but that are part of the chapter 14. So it is important for that chapter that you go to the lecture videos and that you watch the lecture videos. So let's see here the YouTube channel playlist for chapter 14. The sections in the textbook that are pertinent are sections 3 and 4 of chapter 14. But for the videos, it's covered in the videos, except that the video 3 on molecular polarity is not covered in the textbook. So this is one that you absolutely must watch. The third video on molecular polarity, because chapter 14 does not cover that in the textbook. So I would recommend, I would highly recommend to actually watch all the lecture videos of chapter 14 and not rely on the textbook for this chapter. So otherwise, in the Canvas chapter 14 module, there is this document called Electronegativities and Molecular Geometry that you will need to decide if the molecules are polar or not. And that will also depend on the shape of the molecule. So I will use this document for this chapter review. So this is the document on electronegativity values and how to classify a bond from the electronegativity difference between two bonded atoms. And then at the bottom of that Word page, you have the table to help you decide the shape of the molecules. And so that's something you will still need in chapter 14 when you need to decide if the molecules are polar or not. So let's start the chapter 14. And the first question, so chapter 14, the title is Liquids and Solids, and it's mostly on intermolecular attractive forces, which are what holds solids and liquids, into their physical states. So that's why it's all about these intermolecular attractive forces. And so the first question is asking to list and classify the 3 types of intermolecular attractive forces that can act on a given substance and do that in order of strength. So there are 3 intermolecular attractive forces. And so let's understand what intermolecular forces are. Inter means between, molecular refers to molecules. So it's forces of attractions, that act between the molecules and hold the molecules together. It's not bonds, right? It's not bonds, even though you will see one of them has the name bonds, it's not bonds. And so the weakest intermolecular attractive forces are the London dispersion forces, also called sometimes van der Waals forces, and they are due to instantaneous dipoles. It's when the electron cloud in the molecules is, not, homogeneously distributed, and you have some you lack electrons in one area and you have more electrons in another area, and that creates what we call instantaneous dipoles, and then these are attracted by other instantaneous dipoles in a neighbor molecule, and so these are then London dispersion forces. And they are very transient. They constantly change because those electron clouds, they keep moving. And so the instantaneous dipoles keep changing. So that's the weakest of the intermolecular attractive forces. After that, we have the dipole-dipole interactions. These, so let me back up here. London dispersion forces happened for all molecules. It doesn't matter what kind, all molecules experience that because they all have an electron cloud, right? All molecules are made of atoms and all atoms have an electron cloud. And you know, these electron clouds can be distorted, and so that's why all molecules experience London dispersion forces. Dipole-dipole interactions can only happen for polar molecule only. Because dipole suggests that you have a dipole, and a dipole is when you have a polar bond, and that's, you know, one polar bond is a dipole, another polar bond is another dipole. And so when you have molecules that have polar bonds, they have dipole, and they will be attracted, the dipole of one will be attracted to the dipole of another, because you know, positive charges are attracted by negative charges. The difference with the instantaneous dipoles is that these dipoles are permanent, and so it's a stronger force because of that, because it's always there, and so there is always that attraction between you know, positive and area of a molecule towards the negative area of another molecule, you know, a neighboring molecule. Then after that, you have the hydrogen bonds. And as I said, it's not bonds, you know, even though it's called bonds, these are not bonds like the ionic bond or covalent bonds. It's intermolecular attractive forces. It's between two different molecules, or, you know, two molecules of the same substance, but two neighboring molecules. And so these hydrogen bonds are very strong compared to the other forces, but they can only happen when you have hydrogen bonded to oxygen, fluorine, or nitrogen. If you do not have an hydrogen bonded to an oxygen, a fluorine, or a nitrogen, you cannot have hydrogen bonds. That's just as simple as that. So only tell me that you have hydrogen bonds for molecules that do have an hydrogen bonded to an oxygen, a fluorine, or a nitrogen. And so, as I said, these are the strongest intermolecular attractive forces of the three. So that's the three types. And in the lecture, you will hear about ion dipole intermolecular attractive forces. But these they are also a special case because they can only happen between an ion and a dipole of a polar molecule. So it's between two different substances. Because these forces here, we will study them mostly in the context of, you know, one substance. So we will look at, do we have these forces between molecules of the same substance? Of course, they also happen between molecules of different substances, but at first we need to learn for molecules of the same substance. What do we have? What kind of bonds or intermolecular attractive forces? So, which are stronger, intramolecular forces or intermolecular forces? So, please read this carefully. This is intra, and there it's inter, which is two different things. Intramolecular forces are bonds, you know, ionic bonds, covalent bonds, and intermolecular forces are what I listed above. So for a given molecule, which are stronger, the intramolecular forces or the intermolecular forces? Well, let's see that. So intramolecular forces are stronger for a molecule because that's what holds the molecules together and make the molecules. So intramolecular forces are the ionic bonds and covalent bonds, and they are the strongest between the two. Intermolecular forces are attractions only, and so they will be weaker than intramolecular forces because intramolecular forces are what makes molecules, so you want these to be much stronger. Intermolecular forces, you will see that's the forces of attractions that will, decide if you have a liquid, a solid, or a gas at room temperature. So let's look at the diagram here. And so the diagram is here on the right. And it's asking, in the following diagram, which lines represent the hydrogen bonds? So you see those, these are molecules of water. We have one oxygen and two hydrogens bonded to that oxygen. And then we have intermolecular attractive forces. And so the question is, which lines or dots represent the hydrogen bonds? So you have the choice between the dotted lines between the hydrogen atoms of one water molecule and the oxygen atoms of another water molecule, or the solid lines between an hydrogen atom and an oxygen atom in the same water molecule. Both lines represent hydrogen bonds, the solid lines and the dotted lines, or there is no hydrogen bond represented in the diagram. Okay, so the water molecule contains hydrogen bonded to oxygen, and above it's still there. We see that hydrogen bonds can only happen when you have hydrogen bonded to oxygen, fluorine, or nitrogen. And here we have two hydrogens bonded to an oxygen, so we can have hydrogen bonding. So answer D would not be correct. There are hydrogen bonds. And C cannot be correct because they have been represented differently to represent different things. So C is not correct either. So what is it? The solid lines between an hydrogen bond, an hydrogen atom and an oxygen atom in the same water molecule. Same water molecule. So this is the covalent bond. This represents the covalent bond between H and O that make the molecule, right? And so let me put that in blue so we see what I just added. So these solid lines between the hydrogen and the oxygen are, representing the covalent bonds between hydrogen and oxygen that are making the molecule H2O. And so these are what we call, these are the intramolecular forces, we can say. Okay, so these are intramolecular forces. They are not the intermolecular forces, so that's not the correct answer there. So the dotted line between the hydrogen atom of one molecule and the oxygen atom of a different molecule, these are what let me say that this is the right answer. This is what represents the hydrogen bond. It's those dotted line between two different water molecules. That's very important here. It's between two different water molecules because intermolecular forces are acting between two different molecules versus intramolecular forces are, making up the molecules. So hopefully you see the difference here. So question 4, does the nature of intermolecular forces change when a substance goes from a solid to a liquid or from a liquid to a gas? What causes a substance to undergo a phase change? So remember what phase change means. Phase change means a change of a physical state or, physical phase. So it's what is described above, going from a solid to a liquid or a liquid to a gas or vice versa, right? Or a solid to a gas. And so does the nature of the intermolecular forces changes when a substance undergoes a phase change? Yes, definitely. Because intermolecular forces are what's holding the molecules, different molecules together. So let's have this here. So intermolecular forces are what's holding the molecules into the solid phase. It's what will hold, for example, the water into the ice phase, or the water molecules into the liquid phase. So you need those forces. That's what will determine actually the physical state of your substance at a given temperature. And the stronger the intermolecular attractive forces, and the more chances you have solid. So the solid phase has stronger intermolecular attractive forces than the liquid phase. And the intermolecular forces in the gas phase are inexistent. They are not really happening. And that's why you have a gas, because in the gas phase, molecules are free from each other, they are flying around, and there is no repulsion and no attraction between the molecules. And that's what is, by definition, a gas. So there is no intermolecular attractive forces in a gas phase. And that's why, this chapter is titled Liquid and Solids, because intermolecular attractive forces are the reason why, a substance can be a liquid or a solid. So the intermolecular attractive forces start acting out in the liquid phase to bring the molecules back together. So they are holding molecules together. But the molecules, even though they are packed together again, it's random, right? There is no order. And so it's the forces when they become stronger and they try to organize the molecules that you get the solid phase. Because remember, between the liquid phase and the solid phase, the difference is the fact that the molecules are packed, but randomly in the liquid phase, and in an organized fashion in the solid phase. And so for this, you need even stronger intermolecular attractive forces when you are in the solid phase. So, and that's what, is holding the molecules in place. That's why you have solids that, keep their shape, right? It's because these intermolecular attractive forces are holding the molecules of a substance together. And so then they keep their shape. So if you break the intermolecular attractive forces, this will change the solid into a liquid. If you break, some of them, but not all of them, you change the solid into a liquid. And if you break all of them, you change the liquid into a gas, right? It's progressively becoming a gas if you remove all intermolecular attractive forces. So let's keep going with question 5. So the question is asking, true or false, methane, which is a CH4, is more likely to form stronger hydrogen bonding than is water, H2O, because each methane molecule has twice as many hydrogen atoms. Provide a concise explanation of hydrogen bonding to go with your answer. So is it true or false that methane will have stronger hydrogen bonding than water, because it has more hydrogen atoms? Well, no, it's false, right? For hydrogen bonding, we said we need hydrogen to be bonded to oxygen, fluorine, or nitrogen. And here, all the hydrogens are bonded to the carbon. The methane is simply carbon in the center, surrounded by 4 hydrogens, bonded to the carbon with single bonds. There is no hydrogen bonded to oxygen, fluorine, or nitrogen. So you cannot have hydrogen bonding in methane. However, in water, we saw how we have hydrogen bondings because we have oxygen bonded to oxygen. Hydrogen bonded to oxygen. So CH4 does not experience hydrogen bonding because hydrogen bonds can only happen when you have hydrogen bonded to OF or N. However, water experiences a lot of hydrogen bonding, and this is the reason why water is a liquid at room temperature. Yes, because water experiences those hydrogen bonds, and that's the strongest of the intermolecular attractive forces. And so it will keep the water molecule, which is a small molecule, it will keep it in the liquid phase at room temperature, which is very unique for small molecules like water. Because indeed, what happens for methane? Methane is a gas. It's the main ingredient in natural gas. So methane is a gas at room temperature because it's a small molecule, and it only so it's a non-polar molecule. So it only experiences the London dispersion forces, right? Because it's non-polar. And as any kind of molecule, it will experience London dispersion forces, but it cannot experience dipole-dipole interactions because there is no polar bonds in there. And it cannot experience hydrogen bonding because there is no hydrogen bonded to oxygen, fluorine, or nitrogen. So it's only held very weakly by London dispersion forces. And so then molecules that have enough energy can break free from those forces of attraction and be in the gas phase. And so that's why methane is a gas at room temperature, while water is a liquid at room temperature, even though both are very small molecules of similar size. So question 6, determine if the following molecules are polar or non-polar covalent overall. So here, for first molecule we have is a CH3OH, which is a methanol. It starts from methane, and you change one of the hydrogen to the alcohol function, OH, and so that becomes methanol, an alcohol. So we need to decide if it's a polar or non-polar covalent molecule overall. Basically, is the molecule overall polar or not? So for this, you need to do the Lewis structure. And this was part of chapter 12. So here I will bring the Lewis structure, and hopefully it should make sense. So that's the Lewis structure of methanol. So you have carbon bonded to 3 hydrogens and bonded to the oxygen, and then the oxygen is bonded to the last hydrogen. The oxygen has 2 lone pairs, in its and 2 single bonds. So before you decide if a molecule is polar or not, you need to decide, do we have polar bonds? Because if you have no polar bonds, then there's no need to go further. Your molecule will not be polar. So for this, you calculate the electronegativity difference. And as you know, you go through that table. And so between carbon and hydrogen, so 2.5 minus 2.1, that's a difference of 0.4, and that's considered non-polar. And the CO bond, we have 3.5 minus 2.5, that's 1.0. So that's polar. So the CO bond is polar. And then the OH bond, you do 3.5 minus 2.1, that's 1.4, and that's also polar. So we do have 2 polar bonds, the CO bond and the OH bond. So the CO bond and the OH bond. And so then we need to determine the shape around that oxygen, because that's key to know if it will be polar overall or not. So then we need to use the table that helps us determine the shape. And so first, let's count the electron groups that are around oxygen. So focus on oxygen, And let's count. We have 2 single bonds, so that's 2 electron groups, and then 2 lone pairs, that's 2 more electron groups. So we have 2 plus 2, 4 electron groups around oxygen. And among those, we have 2 lone pairs. So let's look at the table of molecular geometry here. And so you want to look at the row that say 4 electron groups with 2 lone pairs. So the last row at the bottom of the table here with 4 electron groups, 2 lone pairs, that's a bent shape. And the angle will be less than 109.5. So it's a bent structure for oxygen. So which is nice that this is drawn like this, because it really shows how it's bent. So even though the carbon here is not represented as a tetrahedron like it should be, if we look at just oxygen, you know, we can say that this drawing, it represents what it is. It's a bent structure where the 2 single bonds are bent with an angle of 109.5 because of the 2 lone pairs on the oxygen. So that means if the 2 dipoles, and let me add that, insert. So I've drawn 2 arrows here to show how the dipoles for the CO bond and the OH bond are. So the arrow that follows the CO bond represents the, you know, that polar bond, and it's pointing towards oxygen, because oxygen is the most electronegative element of the, you know, carbon and the oxygen. And then between the hydrogen and the oxygen, you point the arrow towards oxygen again, because oxygen is the most electronegative element between hydrogen and oxygen. And so because it's bent, you see that those 2 arrows, they will not cancel, right? They would cancel if they were exactly opposite each other, you know, facing each other, or, you know, looking away from each other in a straight line. But here they actually will, combine into a larger dipole. And let me show what we call the net dipole, which is the arrow that represents how these 2 arrows will combine into a larger dipole. That is the dipole for the whole molecule. So you see that larger arrow, how it's like, you know, the 2 little arrows added up together. And this larger arrow represents the net dipole, which means the dipole for the polarity of the molecule as a whole. So then that means the molecule as a whole is polar. So that answers this question. So the CO and OH bond are polar, and they don't cancel out due to symmetry. Instead, they add up. And so the CH3OH molecule is polar overall. And that's, you know, these 2 polar bonds do not cancel because the shape around the oxygen is bent with an angle of 109.5. And that's because oxygen is surrounded by 2 single bonds, 2 lone pairs, which is a total of 4 electron groups, but with 2 lone pairs. So then that makes a bent shape. So that's why, as you can see here, Chapter 14 will not show you how to decide if a molecule is polar or not, like I just did. So it is important that you look at the lecture videos, especially video 3 for chapter 14. So let's do now Bf3. Boron bonded to 3 fluorine. Okay, so let's look at so first the periodic table. Boron is a metalloid. Fluorine is a non-metal, right? Hopefully you have seen them here, boron, and then fluorine. So boron has 3 valence electrons being in group 3A, and then the fluorine have 7. 7 times 3 fluorine, that's 21 plus 3, 24 electrons. And so if you do the Lewis structure of Bf3, you will come up with this. So here I brought the Lewis structure of Bf3. So we have 24 electrons in that structure. If you count from the lone pairs on the 3 fluorines, you have 6 pair, fluorine times 3, so 18 electrons there, plus 3 single bonds, that's 6 more electrons, so 18 plus 6 is 24 electrons. And notice how the fluorines have an octet, 6 electrons from the lone pairs plus the 2 from the single bond, that's an octet for fluorines. However, boron is an exception and will only need 6 valence electrons around it to be a stable molecule here. It's an exception, so you have to know that this is an exception and will only require 6 valence electrons around it. So that's the Lewis structure of Bf3. So now we need to decide if we have polar bonds. And so we do have the Bf bond. And let's see, from the electronegativity difference here, F is 4.0, B is 2.0, that's a difference of 2.0, which is a large difference, and that's usually considered ionic. However, we know that boron is metalloid, fluorine is a non-metal, so together they make a covalent bond. So even though the electronegativity difference is above 2. So it's polar. Even though it's not ionic, it's very strongly polar towards the fluorine. So right, so the Bf bond is polar, and if you draw the dipole arrow, you would show the arrow, and let me steal it from here. You would do it like this. It's, pointing towards the fluorine. And then the third one going here, this way. Okay, so you have 3 polar bonds, they each go towards fluorine because fluorine is the most electronegative element of the 2. However, you need to take into account the shape of the molecule and see if these dipoles, they will add up or will they cancel out. So we need to decide the shape around the boron. So we count the number of electron groups around boron, and here we have 3 single bonds, so that means 3 electron groups. So let's look at the table and decide what is the shape when we have 3 electron groups, 0 lone pair. So here, in the middle of the table, start with 3 electron groups, 0 lone pair, and the molecular geometry is trigonal planar. And you have a model here showing how the purple ball that is the central atom is in the center, and it's surrounded by 3 green balls equidistant from each other, forming a triangle. And the bond angle is 120. So this is a very symmetrical shape, and the fluorines are, equidistant from each other and as far away from each other as possible this way. So the shape looks like this. Let me draw that. So I brought a model of the Bf3 molecule with the proper shape. And you notice here how the fluorines are farther apart from each other if you put them like this in a triangular shape around the B. And they are at 120 degrees from each other. And so now then we have these little dipoles, and let me orient them properly. They will go like this. One goes straight up, and then the third one goes like this, from B towards F. And I should put them with the same length, because these are 3 fluorines coming from boron. So the 3 arrows should have the same size, because it's the same type of bond. So BF, so same size of polarity. And because this is a symmetrical and flat, right? It's flat, trigonal planar. So these dipole will cancel out. If you imagine that you are pulling on the direction of these arrows, and pulling equally in those 3 different directions, you will see that you can imagine that your molecule will go nowhere. It cancels out, and overall the molecule is non-polar. So here it summarizes what we saw. Bf3 has 3 electron groups around B, the central atom, and so it's trigonal planar, right? It's flat. And so because of that, it will be non-polar overall, because the 3 polar bonds are identical and pulling in opposite directions symmetrically around B. And so their dipoles are canceling. I know it's hard to imagine, but they do cancel out because they have the same length, same strength, and they are pulling symmetrically, in the same plane of the molecule. So then overall BF3 is nonpolar. So we'll continue question 6 with Cl2O and SiF4 on Thursday at the next Zoom meeting.